Today what I'm going to present you is something like we want to establish which GPU card between NVIDIA and AMD performs better in terms of timing performance and reliability. In addition, we want to evaluate which approach is the best one to evaluate reliability for GPUs. And first of all, I want to thank my co-authors from University of Athens, Dimitris Gizopoulos and Sotiris Tselonis, and Stefano di Carlo from Politecnico di Torino. So, nowadays we have foreseen that application has become more complex and we need a lot of computational power, and GPUs have been proposed as a solution. However, at the beginning these devices were just employed for gaming and graphical application, but nowadays they find application also in fields where reliability is a top concern. So one question, one challenge nowadays is to evaluate which GPU architecture perform the best in terms of reliability and performance. This is the outline of my presentation. At first I will introduce the state-of-the-art works, then I will talk about my contribution, which is a reliability framework evaluation. There will follow experiments and conclusions. So in literature there are many reliability evaluation tools, both for NVIDIA and AMD GPUs, and some of them have some lacks, and others have some features that make them the best. For example, we have GPU Soda, which is a microarchitecture level ACE analyzer for reliability, which is based basically on PTX assembly, which is far from the assembly that is executed on the real GPU. For NVIDIA, we also have two other evaluation tools, which are Goofy, which is a microarchitecture level reliability framework, which is based on a microarchitecture simulator, which is GPU Sim. Then we have Sassify, which is a very, very fast fault injector in real hardware. However, the target components for reliability issues for this simulator, for this reliability analyzer, are limited. Instead, for AMD GPUs, we have some works available from literature. For example, at CELSE 2012, it was proposed a fault injector for evergreen AMD GPUs. And then we have CIFI, which is a Southern Island AMD microarchitecture level ACE analyzer and fault injector. So in this paper, in this presentation, I will talk about my contribution, which is the comparison, a joint evaluation of reliability and performance for NVIDIA and AMD GPUs. And I will compare also the two different approaches, which are ACE analysis and fault injection. And finally, what I want to highlight are software and hardware masking properties for these devices. So let's talk about the reliability framework. Basically, we performed our analysis on the basis of two tools, which are CIFI for AMD and Goofy for NVIDIA. They are both based on two microarchitecture simulators, which are Multi-to-Sim and GPU Sim, and they have been tuned in order to perform both fault injection and ACE analysis. At the end of this evaluation, we are able to provide some metrics in terms of reliability and performance. First of all, we analyze architectural vulnerability factor, or AVF, which is the probability of a fault to manifest as an error at the output of the application. Another metric that we consider is AVF util, which is very similar to AVF, but instead of considering all the faults happening in the hardware resources, we just consider the faults that happen in resources that are used in the context of the application. And then we have failure in time, which is the number of expected error of the application in 1 billion hour of operation. And finally, we consider execution per failure, which is a metric that counts how many execution a device can perform before a failure happens. So basically, this is a picture of the microarchitecture of Southern Ireland, but we can also bring the one for NVIDIA, which is quite similar. And we have identified some hardware structures that are common for both the architectures. And so we, in our analysis, we evaluate reliability, considering faults happening in local memory and in the vector register file for people that are more common with NVIDIA names. Local memory is called shared memory, and we selected these blocks because their area is quite big, so faults are most likely to happen in such kind of hardware structures. Moreover, by disabling error correction code for these hardware structures, we can save some power. So this is the fault injection framework. Fault injection consists of several steps. We have modified the fault injection process in order to speed it up. So at first we run a profiling of the application in which we estimate the time interval in which kernels are executed, and we gather the output of the golden simulation. Then next step is the fault generation. So we generate faults with a uniform distribution for time and space. Then these faults are profiled and they are classified as util injection or non-util injection. A util injection is an injection that strikes a hardware resource that is used in the context of the application. Then we run parallel fault injection just for util injection, since we know a priori that not util injections are masked for sure. And finally, what we have, we get error classification and we generate the reliability report. So here, instead, on the opposite, we have the ACE analysis framework, which basically aims at identify the ACE bits per clock cycle. ACE bits are the bits that must be correct in order to have the output of the application correct. So if you look at the slide, you can see that there are some time intervals in which bits are considered ACE or an ACE. Then, after that, we can combine the ACEness, the average number of ACE bits per clock cycle, and we can gather information about AVF and AVF util. This kind of ACE analysis does not take into account dead instructions and logic masking, so we perform a pessimistic evaluation for reliability. However, this analysis is very fast. And what I can add here is that dead instructions for GPUs are very, very low, and their contribution to reliability is negligible. So these are the experiments that we performed on 10 benchmark from AMD Apple SDK and CUDA SDK and Rodinius benchmarks. We considered 4 different GPU architectures. For NVIDIA, we considered the G80, GT200, and Fermi, while for AMD, we consider Southern Island architecture. For fault injection, we performed 2 2000 injection per structure, and these are the results. First of all, what I want to show you now is AVF for register file. We computed it with fault injection, that are the black bars of the graph, and for ACE analysis, which are the white bars. In this case, you can see that ACE analysis can provide an overestimation for reliability. And what we have noticed here is that one of the main contributions to AVF is given by occupancy. Occupancy is the number of resources that are used in the context of the application, divided by the total number of hardware resources that are present in the GPU device. So in this case, what we can say is that to have a better insight about reliability, we want to decouple the occupancy from AVF. So here there are results for AVF util. In this case, results are not influenced by occupancy. And here you have a better insight of what is the software and software masking properties of the GPU. What we can see from this graph is that reliability is workload dependent, of course, and masking properties are dependent on the applications, and there are also differences among the different GPU architectures that are due to the fact that these architectures have different microarchitectural parameters, such as the number of sync unit and the size of the register file, and other things like that that influence the scheduling and the vulnerability at the end. So here, what about having a global picture of the reliability of the entire GPU architecture? Here I present the failure in time, considering the contribution of the register file and the local memory. The register file is in black, while the local memory is in white. Here, what we can see is that for most of the application, reliability is influenced by the contribution of register file, while just for histogram, local memory plays a key role, and this is due to the fact that local memory, in this case, it's used just a read-only memory. So here we can answer the question, what is the best device for reliability? And in most of the case, the Southern Islander Radeon 7970 is the best one, while for NVIDIA we can say that the Fermi architecture GTX 480 has the worst behavior in most of the cases. However, we have to evaluate jointly reliability and performance. So we want to consider also the computational power of the devices and how this correlates with the reliability. Finally, I present the execution per failure, which combines reliability and performance. And here you can see that Fermi architecture is from the last position in the failure in time gains some positions. This is due to the fact that a large number of execution due to the computational power of such a device allows the Fermi to increase its performance. So the lesson learned here is that higher parallelism translates into more performance and higher execution per failure. So this concludes my presentation. Here I have presented you an analysis, a comparison between AMD and NVIDIA GPU architectures. for 10 benchmarks, and we also have compared the performance of two different reliability evaluation approaches that are fault injection and trace analysis. And I've showed you the masking properties of software. And this concludes my presentation. And I want to thank you, and if there are some questions, I'm pleased to answer. Thank you.